Heyo, it's Mr. Otwell, the Math Master, helping you master math. And today we're going to look at part one in discovering properties of the exponential function. Let's do this. In order to find our beautiful and amazing properties of exponential functions, we want to look at the three main ways we represent a function: an equation, a table, and a graph, and see how they all tie together. Remember, these are all just different representations of the same information. So whatever data we can gain from this equation will be the same as the table, will be the same as what's on our graph. So really, we want to have all of this information together to really help us know about the function's domain, range, y-intercept, asymptote, all the good stuff that we need to know about the function. Let's take a look at our equation. The reason this is an exponential function is because x is our exponent. Our independent variable, what we're plugging things into, is the exponent itself. That's what makes this an exponential function. So what we want to start doing is checking when b is greater than 1. Okay, we're going to play around with b a little later, but generally speaking, when we want to look at properties of the exponential function, when b is greater than 1, we just choose 2. It just makes our life easier. So if we choose b to be 2, then this means that our function f of x will be 2 to the power of x. So remember, this is function notation. The f is just kind of the name of the function. X is our independent variable. That's what we substitute values into. And then here is our function. This is defining what we're going to get as an output. Anywhere we see an x, we're going to substitute it in right there. So really, I've chosen some x values here for our table so that we can generate this graph, so that we can make the graph. Usually, if you have a parent function, just some function where there's only one primary operation with no extra stuff going on, you're not adding more, you're not multiplying more, you want to know what's happening at 0. And you really want to know what's happening around 0. So you just kind of start from there and see what happens in order to determine the properties. You can choose whatever x values you want, but these are going to help us out a lot. So why not just start at 0, right? If we want to know what our output is, so here's our x values in this column and our f of x values, these are just y's, these are what we get after we plug in these numbers. We can just take all these x values, substitute them in to our function f, and then plot all of those points. So why not just start at 0? If we wanted to evaluate f of 0, we take 0 and substitute it into our function f. I'm just going to write my function f here again, just so that it's easy to reference. We're going to take a 0, and everywhere we see x, we're going to substitute in 0. So we have 2 to the power of 0. And that gives us 1. If you want to know why that's 1, you can go check out my other videos about exponential properties and simplifying radicals. I'll link those down in the description. You can go check those out. So when we substitute 0 into the function f, we get 1. So when x is 0, f of x is 1. And we continue this process. We can substitute in 1, so that would give us f of 1 is equal to 2, because that's our b, we didn't change it. And then instead of an x here in our parent function, we're going to substitute in 1. And 2 to the power of 1 just gives us 2. So when x is 1, we know f of x is 2. And we continue this for 2 and 3. So really quickly, I'm just going to go ahead and evaluate these, get us some values here, and we'll come back for the negatives. So we found that when we substitute in 2 and 3 into our function f, we get 4 and 8. So I went ahead and wrote those values here. But what about our negative numbers? In the same way we substituted these into f to see what happens, we're going to take -1 and substitute it in. So everywhere we see an x, we substitute in -1. So remember, if our exponent is a negative number, that's going to take the base and flip it. It's going to give us the reciprocal. What we need to keep in mind is that x to the negative a power, when a is just any real number, that's going to give us 1 over x to the positive a. What it does is it takes our base and flips it down to the bottom, or if it's on the bottom, it flips it to the top, and changes our exponent from negative to positive. So in this case, if we have 2 to the negative 1 power, that's going to flip our 2 down to the denominator. It's going to give us the reciprocal, and our exponent changes from a negative 1 to a positive 1. And 2 to the 1 power is just 2. So when we substitute negative 1 into f, that's just going to give us 1/2. I'm going to go ahead real quick and substitute in negative 2 and negative 3, and we'll be right back. So really quickly, just to remind us of how I got all these numbers, when we have negative exponents, it takes that 2 as the base and brings it down to the denominator, and it changes the exponent from negative to positive. And we know that 2 squared gives us 4, so this ends up giving us 1/4. In the same way, this negative 3 exponent, that takes the 2, flips it down to the denominator, changes that negative 3 into a positive 3. So we know now that 2 to the third power is 8. So our 1 is still on top. Nothing got changed there. This will become 1/8. So now we have a nice little table of values. We want to graph those so that we can analyze this function a little better. We're ultimately trying to determine some properties about it: the domain, the range, y-intercept, and asymptote. And the best way to do that is the graph, honestly. What's easier to think about? These abstract ideas of what we need to consider given our function in equation form, or a nice visual representation of the function as a graph? I would say the graph would be really great. So what I like to do personally is when I'm looking for domain, range, all this good stuff, I'm going to be taking a look at my graph just to give me that visual idea of what I'm dealing with. So remember, when we graph something, we want to take our x and our f of x values and make those an x and a y on the graph. As you'll notice, this horizontal axis is the x-axis, and this vertical axis here is our y. Y is the same as f of x. It's just different notations to say the same thing. Y is an output, f of x is an output. So these are coordinate pairs. So when we have x as negative 3, we get 1/8 as an output. So we start at the origin, 0, 0. We move left 3 because that's our x for negative 3. And then we need to go up 1/8. One's here, 1/2's about there, 1/4. Oh, let's go right there, 1/8. So it's really kind of close to 0, but it's not quite there. We're just approximating here. We're getting it close. Our next point is negative 2, 1/4. So we go from 0, 0 to negative 2 and up 1/4. So it's a little higher, not quite to a half yet, but a little higher. Then we have negative 1, 1/2. So we go left 1 and up 1/2. Then we have 0, 1. So 0 on the x, we're not going left or right. And then we go 1 up. Then 1, 2 will be right 1, up 2. We have 2, 4. So when x is 2, y is 4. We go right 2, up 4. And 3, 8. When x is 3, y is 8. Oh, it's way up here. We can just say, oh, it's about there. Why not? That would be 7, that would be 8. Hey, why not? It goes off the graph, but we're fine with that. So as you can see, the dots generally go up there. You don't really want to connect these with straight lines. This is clearly making some sort of curve. So let's connect our points and make that shape. So now the question would become, well, what's happening down here? Is it going to hit 0? What's happening? Well, let's think about it. If at negative 3 we got 1/8, as we put in smaller x values, so as those negative numbers keep getting bigger, the output goes from 1 to 1/2. So it got smaller, got closer to 0. Then it goes from 1/2 to 1/4, closer to 0. 1/4 to 1/8, closer to 0. So what do you think is going to happen if we plugged in negative 4? Once again, they get even closer to 0. But here's the question, right? Is there some negative number that we can substitute in so that we actually get 0? Is that possible? Is there some x that when you plug it in to the exponent, this whole thing gives us 0. No, that can't happen. We can already see that positive numbers just make this thing bigger. We know that 0 here gives us a 1, so that's not 0. And what we're finding is as we plug in negative numbers, it's just getting closer and closer to 0, but never happens. This will never happen. There is no value of x that will give us a 0. So what's happening there? You guessed it. We have an asymptote. There is an asymptote on the x-axis. So when we're graphing that, usually we will represent it as a dashed line on wherever the asymptote is. For our case, it's at y equals 0. This function will never equal 0, ever. So what the function is doing is it's getting really close to 0, but it'll never touch it. That function approaches the asymptote, but will never touch it, okay? Sometimes there are asymptotes which actually the function does touch it, but basically as the function tends to infinity, or as it goes on forever, the function will approach the asymptote and never touch it. So here's the graph of our exponential function, f of x equals 2 to the x. So now we have a nice, beautiful picture representing our function. We have our function represented as an equation. We have our function represented as certain inputs and outputs on a table. And we have our function represented here as a graph. So now let's talk about the domain, range, y-intercept, and asymptote. So remember, domain is all possible input values of your function. In this case, our inputs are x's. So we're just wondering, what are all the x's we can plug in? Range means all possible outputs of your function. In our case, outputs are y values. So we're just asking, what are all the possible y's that we can get with our function? If we're able to have our equation, table, and graph at our disposal to determine domain and range, in my opinion, the best thing to look at is the graph, because it's a visual representation of all of your inputs and all of your outputs. So domain is all possible inputs. We already said our inputs are x values. So if we follow this curve right here, our green function, what are all the possible x values that it can take on? Well, really, if you just ask yourself, how far to the left does this go? If you look at this function as it goes forever to the left, where does it stop? Are there any x values that you won't get to? Well, this arrow means it goes on forever. So it's going to go forever to the left. So the smallest value that our domain can be will be negative infinity. It can be 0. So now if we just ask ourselves, how far right does it go? How far right does it go? That can tell us the highest possible value of x it could take. Because this arrow here means it goes on forever. Yeah, I mean, it's going up a lot faster than it's going right, but, you know, it's still going to go right forever. So this will never stop. Therefore, the highest value of our domain is positive infinity. So this would be our domain in interval notation. Remember, with interval notation, we're going to put the smallest value in the left part of the comma, the greatest value in the right part of the comma, and the symbols on the left and the right will either be a parentheses or a brace. Remember, parentheses means it will not equal whatever that value is, and the brace will mean it can be equal to whatever that value is. Infinity, we can never actually equal infinity. Therefore, if we ever write negative infinity or infinity, we always use a parentheses for interval notation. Now let's talk about the range. If the domain was all the x values for this function, and the range is all y values, before we were asking how far left and how far right. Well, now we want to ask how far down does this go and how far up does this go? The green function, what's the furthest down it can go? Oh, what's happening? What's happening right there? The asymptote is stopping it. It cannot go further down than where the asymptote is. Therefore, it is going to approach 0, get really close to it. But will it ever equal 0? No, it won't. So the smallest value of our range will be a 0. And as we mentioned, it cannot equal 0, so we'll use our parentheses. What's the highest this function goes? The highest it goes, because that will be the highest value of our range. Well, as we mentioned, the arrow means it goes on forever, so the highest value of the range will be positive infinity. And we always use a parentheses for infinity in interval notation. So here's our domain. Here's our range of our exponential function. So our y-intercept, remember, our y-intercept is the value where our function intercepts or runs into the y-axis. So where does that happen? Bam, right there. So the y-intercept is 1. The coordinate point itself is 0, 1. The asymptote here, we've already mentioned, it's right here. But we always want to represent our asymptote as the line that it is. In this case, this horizontal line that goes through 0 is the equation y equals 0. Because every single y value on this line is equal to 0. So that's going to wrap it up for part 1 of our Discovering Exponential Function Properties videos. We kind of laid the foundations here of all the things we want to be looking for. But in the next couple of parts, we'll check out what if we have a negative x? What if our base isn't bigger than 1? What if it's in between 0 and 1? So once those videos are finished, I'll put a link down in the description. You can check those out. Hopefully you found this helpful. If you did, please subscribe. Please like, please leave a comment if you have any questions. Mr. Otwell, out. Peace.